Okay, so first of all, thanks to Chris, thanks to Nick for inviting me to come speak. So earlier, Jeff said that people later would talk about the more technical points, and I'm not actually going to talk about the technical aspects of holography beyond what's required, for our discussion. The talk is very much aimed at a mixed audience, but I will assume that everyone knows a little bit about gauge theory. That's the only thing I'm going to assume. Okay, good. So if you look at the title on the website, it said Philosophical Perspectives on ADS-CFT. At some point I realized that ADS-CFT was just too darn complicated. So I decided to talk about a toy model that's not ADS-CFT, but where you still see holography. And I'll make a couple of remarks about ADS-CFT maybe right at the end. So, now the purpose of this talk is not to add anything new to the physics literature or to tell physicists how to best advance in the search of quantum gravity or the construction of ADS-CFT duality. Rather, the first and primary purpose is to try to make a first stab at answering the question, what is the philosophical interest of holographic duality? And I'm going to try to answer this question by making connections with two already extant themes in the philosophy of physics literature. So, so you may ask, well, what do I have to say to our friends and colleagues in physics? And I guess the hope is that you will find these issues inherently interesting. Not just interesting because they're going to help you advance the search for a theory of quantum gravity. The second question, so is more particular. It's what is the relevance of holographic duality for the philosophy of quantum gravity? And I'm not going to pretend to come anywhere close to answering number two. I think it's very much an open question, but I'm going to say that it will be partially answered by conceptual analysis of what one is doing when one tries to construct a holographic duality. So in part, it's going to be answered by reference to the first point. Good. So the strategy is to do a case study. Instead of considering the full ADS-CFT correspondence, we'll focus on one of its precursors, namely what's called, well, it seldom goes by this name, but I've called it by this name because I think it's the most descriptive, the 3D gravity/CFT correspondence. So in the literature, it's sometimes known as Chern-Simons CFT, where it's assumed that the Chern-Simons theory is a stand-in for 3D gravity. And so what is this correspondence? The first thing to be clear on is that it's a conjecture, very much a conjecture, like ADS-CFT. I don't think it's anywhere near being proven, but I think Jeff is in a much better place to remark on that. And roughly it says that three-dimensional general relativity with negative cosmological constant is equivalent to an appropriate conformal field theory on the boundary of an asymptotically ADS manifold.
Sorry, is it 3D means 2 plus 1?
3D means 2 plus 1. Yeah. Yeah, so I say it's simple, but in fact it's still not that simple. So let me just flag as an issue first that in the literature, not just in this talk, but in the literature, there is no consensus about what exactly 3D gravity is, 3D quantum gravity, nor is there consensus about what the appropriate conformal field theory is. Okay? So, but we're just going to proceed as if it's not just conjecture, as if we've resolved this issue, as if the duality exists. And the reason for doing so is because I want to try to pose a counterfactual question. So, were it, not necessarily counterfactual, but yeah, were it the case, in the subjective mood, were it the case that this duality exists, what would be learned? So, what kind of philosophical significance would it have? So, I won't return to this later, but I'll just now flag the conceptual problems to the conjecture. So first off, 3D gravity is not obviously equivalent to Chern-Simons theory, and that's a bit of an understatement. It's been a common move to try to turn 3D gravity, Einstein gravity, into a Chern-Simons theory because it's much easier to quantize a Chern-Simons theory. But there is a problem in the correspondence between the what you take to be, the correspondence between going from the metric in 3D gravity to the corresponding entities in Chern-Simons theory, which are variously called tetrads, or Villebine, or coframe fields. And the problem is that when you quantize the theory, there's a question of whether or not to include non-invertible Villebine. That's not a problem in 3D gravity, because for the correspondence to be the case, you need to have invertible tetrads, so you can correspond exactly to the metric of 3D gravity. As I've already said, it's unclear which CFT to choose as a dual, and it's also unclear that the conformal field theory correctly accounts for the entropy of the black hole. I'll say more about, this is the first time I'm interested in the black hole. I'll say more about this in just a second. But this is one of the non-trivial tests of whether there's a duality between the conformal field theory and the boundary of ADS space and 3D gravity of negative cosmological constant. So the sources I'm going to use are a long review of this duality by Carlip, 2005, and a paper by Witten from 2007. So it's a really significant paper because in many ways Witten started this cottage industry of talking about 2+1 gravity, and then talking about the duality between Chern-Simons theory and the boundary CFT. He put forward a proposal for thinking about how to quantize 3D gravity in 1988. And in 2007, he revisited the proposal and made some significant amendments. And so most of what I'm going to say in describing 3D gravity is going to draw on this 2007 paper by Witten. So now I'm going to introduce the two philosophical themes, the extant philosophical themes in the literature that I think are connected to holographic duality. The first theme is, what is the physical significance of gauge symmetry? This is an issue that's been discussed by many people in different ways. But I'm just going to highlight, three different strands of literature. So the first is a discussion by these philosophers, Catherine Brading, Harvey Brown, Richard Healy, Peter Casso, roughly dating from late 90s to early 2003, where they discuss why gauge symmetry is not like global symmetry. And one of the angles at which they attack this issue is, well, for global symmetries, you can construct analogs of Galileo's ship, but you can't do this for gauge symmetries. Now, there's a second phase of this discussion that was prompted by a paper by Greaves and Wallace that just appeared in BJPS. And so this paper attempts to refute the claims of Brading, Brown, Healy, and Casso, and their colleagues, and it says that, in fact, you can construct an analog of Galileo's ship for gauge symmetry. Roughly, so I'm not going to try to summarize this debate for you, but those of you who are familiar with gauge symmetry should be able to follow the outline of what I'm now about to say. So roughly the angle of attack that Greaves and Wallace is that, yes, you can have gauge symmetries that are physical if you consider asymptotic gauge symmetries of subsystems. There's then a follow-up exchange involving Simon Friedrich and myself, where Friedrich attempts to refute Greaves and Wallace, and I say Greaves and Wallace are mostly right, but not quite. So if you want to ask about this during Q&A, I'll be happy to answer questions, but the point of relevance for us is that it's precisely considering asymptotic gauge symmetries as physical, which plays a huge role in holography, in particular in the 3D gravity CFT correspondence. So if philosophers are interested in interpreting gauge symmetry, there's a natural link there to considering holographic duality as an extension of this. I should also note that there is a different discussion about the physical significance of gauge symmetry by Ravelli. This paper that just came out, 2 months ago, hot off the press, titled "Why Gauge?" And his line in that paper is that gauge-dependent entities contain physical information, truly, but of a slightly different type than most of us are used to considering physical information. They contain physical information about how physical systems could, in principle, couple to other such systems. It's kind of modal relational information. Again, I'm not going to comment so much on this aspect in this talk, but it is related to holography. In particular, we really see the relationship in the ADS-CFT correspondence. Here's the second philosophical theme, which is one that I'm going to dwell on a little bit more. And it's the question, when are two scientific theories equivalent? It's a question that's still very much underexplored by philosophers of physics, especially for specific theories. So a theory of mechanics, for instance. There are some exceptions. So Joe North and Eric Curiel have both written papers about purported equivalence between Lagrange and Hamiltonian mechanics. Roughly, North says that Hamiltonian mechanics is the true ontology of classical mechanics. It's space-based in symplectic forms, that's what it's about. And Curiel says, no, it's Lagrangian mechanics defined on the tangent bundle of space-time. That's the true ontology. The actual debate between them won't concern us. What will concern us is the common assumption that both of them make, which is that in order for two models of a theory to be physically equivalent, they have to be isomorphic. So let's just call this a model isomorphism criterion. The model isomorphism criterion has been attacked in a pretty general way by Hans Helvesen at Princeton. And among other things, his work indicates that one of the ways in which the model isomorphism criterion is insufficient is that we shouldn't just consider models, but also relations between models. And you might think that categorical equivalence, in a sense of category theory, is a remedy for this. I'll say a bit more about this in just a second. But intuitively for now, it's easy to see that there are many things, even in math, that we would like to consider equivalent in some sense, but which aren't isomorphic. So, for instance, the category of topological spaces of a certain kind is equivalent to the category of C-style algebras of a certain kind. They have the same content in a sense, but they're definitely not isomorphic. And there's lots of simpler examples of this phenomenon. Okay, so how does all this stuff relate to holographic duality? Well, holographic duality is and it purports to be some kind of equivalence between models. And I think it's very interesting for us to think about, because it suggests a way of thinking about equivalence that's quite a bit different from these sorts of examples, and much richer in a certain way, much more detailed. So let's think a little bit more about the general framework for talking about equivalence. Let T1 and T2 be our purported dual theories. So how might one formalize equivalence, at least from a mathematical perspective? Naively, you might try to formalize it as given in terms of maps between these two theories that relate their respective physical quantities or observables, and so on and so forth. And there's a precise model that precise formalization that mathematicians have for this idea, which is called categorical equivalence, which gives a precise sense in which these two theories are said to be equivalent. Now, actually, it would be helpful to know, how many people want me to actually explain what categorical equivalence is? Okay, so the quick and dirty explanation is that for a particular mathematical theory of some object, we're used to saying that two things are the same if they're isomorphic. Namely, if there are maps between the two objects that we can compose in such a way that they equal the identity on one object in one direction, and if you do it the other way, they equal the identity of the other object. What categorical equivalence does is it lifts this concept of isomorphism up to the level of categories. So the individual objects don't have to be equivalent, but the categories in some sense have to be isomorphic. So that's the quick and dirty explanation. As far as I know, this is the only really precise mathematical way we have to talk about equivalences between mathematical theories. So it's not implausible to think that, and so I throw this out as a conjecture or as an idea, that the formalization of duality in physics is still at a relatively underdeveloped stage, because were it fully developed, we would have a form of it that looked like categorical equivalence. So anyway, that's a kind of clear and precise mathematical model that we can have for this idea of equivalence. And in the limiting case, you might think that the maps are merely the result of happy mathematical coincidence and some ingenuity. So there are all sorts of examples of categorical equivalence where the objects of two different theories are not actually that different. In fact, they don't even look like different physical theories. They don't look like they encapsulate different physics. In more physical situations, so for instance in mechanics, we're familiar with maps like the Legendre transformation that takes us from Lagrangian to Hamiltonian. And we're also familiar with cases where the map essentially picks out the algebraic structure of functions on some space. So that's a case of C-star algebras and topological spaces. And what I want you to notice is that in this collection of examples, the two theories are individually complete in a certain sense. The maps act on structure that already has a well-defined role in the theory, internal to the theory. And as we're going to see, holographic duality is interestingly and subtly different from this. So we're going to now have a quick review of 3D gravity and CFT. And here's how we start. We start by trying to put 3D gravity into the form for gauge theory. And the first observation is that we can take our usual metric and write it in this form. So what we've essentially done here is to write the metric in terms of coframe fields and then equate it with the usual metric. And so we get this expression here. If we set G ovaline to the Minkowski metric, we now see that we have a pointwise SO21 symmetry. And so we can introduce an SO21 value gauge field, which is often called the spin connection. And that's this guy omega. And the way people usually turn this into a gauge theory is by combining the Vielbein and the spin connection into an object called A, which is going to play the role of our gauge field for the theory. One then notices, and this is one of the central observations of Witten's paper 1988, that if you write down the usual Chern-Simons action for the theory, and this is standard form, the Chern-Simons action, this just spits out usual Einstein-Hobart action. The reason this is not totally conceptually trivial is that the trace that you use isn't the usual trace for Young-Mills or Chern-Simons gauge theory. You've got to make a clever choice of bilinear form, which is this trace here. So the relevant scenario for holography is where we have a negative cosmological constant. And I'll say more about this in just a second. And so for negative cosmological constant, the Einstein-Hobart action has this form. The cosmological constant is -1 of the L squared. So it's in this term here. And the solutions to the equations of motion are constructed by gluing together patches of ADS space. And there'll be a finite number of parameters governing this gluing together. So it's you know, very much a topological theory in the relevant sense. There are no local degrees of freedom, no gravitons. But the remarkable thing is that there do exist black hole solutions, and this was in a primitive form discovered by Bonelli, Banadas, Teitelbaum, and Zanelli. So it's called the BTZ black hole. And you can only find these black hole solutions for a negative cosmological constant. Okay, so let's now try to write the form of the action that we want to quantize. So as we saw, the Chern-Simons action, written in the way I just wrote in the previous slide, gives rise to the Einstein-Hilbert action. But it's also true that you can add a topological Chern-Simons action, people sometimes call it topological interaction, without changing the equations of motion. So this is the most general form of the thing that we should want to quantize in such a theory. There's another move that we can now make from this action. We can rewrite this action as the action of two gauge fields now, A alpha left and AR for right. And here the action takes this form where IL is the Chern-Simons action for the left gauge field, IR is the Chern-Simons action for the right gauge field, and KL and KR are the coupling constants respectively. And so just by some simple algebra, you can rewrite it as this expression here. And it turns out that this bit in parentheses, IL minus IR, gives rise to the Einstein-Hilbert part of the action. And this part here, IL plus IR over 2, gives rise to the Chern-Simons topological part of the action. And these gauge fields take values in SO21 cross SO21. So that's the general picture. What hints at duality? The following things. So first off, for the BDZ black hole solution, you have asymptotic symmetries, asymptotic diffeomorphism symmetries, that form two copies of Virasoro algebra, and which in fact acquire a central charge when realized as canonical transformations. So the two copies of the Virasoro algebras are the holomorphic and anti-holomorphic parts, respectively. And that's exactly the algebraic structure you would expect of a conformal field theory. The second hint is that when you consider, so in order to explain the second hint, I should go back here and tell you that when I initially talked about this Chern-Simons action, I was integrating over a compact closed manifold, and so there's no boundary. In fact, when you have a manifold with boundary, the Chern-Simons action is not quite invariant under gauge transformations. And if you consider what happens when you have a manifold boundary, you see that you induce another action on the boundary. And that's what people call the Wess-Zumno-Witten action. And it's going to be the action for the conformal field theory in the boundary. So together, these two things point towards the existence of conformal field theory on the boundary of this asymptotically anti-de Sitter space. Why? Okay, so let's pause now to reflect on this a little bit. So what have we learned from this? So first off, a dynamical system, or physical theory in itself, model physical theory, is not fully well defined without considering the boundary conditions you put on it. But it turns out that when you consider the boundary conditions for this particular physical system, you get the central algebraic structures for a different theory, a conformal field theory, on that boundary. It's the first thing to notice. This, when the central charge was first discovered, was very much thought of as a curiosity. It's, a curiosity having to do with the mathematical structure of these asymptotic symmetries, and what happened when you tried to realize them as canonical transformations. And it's the point is we're reflecting on is at that point in time, it just wasn't clear how to interpret this algebraic structure that you just get, right? Okay, this thing has this neat Virasoro symmetry, and when you take the Lie brackets, you get a central term. But what does it have to do with the physics of the system? On the other hand, there is a system which we know pretty well, we're pretty familiar with, where the central charge plays an incredibly crucial role. Roughly speaking, the central charge encapsulates the degrees of freedom of a conformal field theory. And so, one kind of interpretation of this holographic duality is that the boundary conformal field theory, in a sense, helps complete the physical interpretation of 3D gravity with negative cosmological constant. Here's another stab in that direction from this 07 paper by Witten, where he explicitly says, so I'll mention also the preamble, where he says, look, we don't know what it means to solve 3D gravity for lambda positive or for lambda 0. But we do know what it means to solve 3D gravity for, yeah, right, okay, for negative lambda. I thought I wrote it wrong. For negative lambda, because the Duality-CFT gives us a way of spelling out the quantum dynamics of the system. And according to Witten, we should interpret that as being in some sense analogous to the S matrix of a regular QFT or quantum gravity theory. And so I'm going to skip this last way in which the CFT completes the interpretation of the gravity theory, because it's a bit technically complicated. So to sum up these 3 points, what's happening here is that, in some sense, you have yes, 2 theories that are conjectured to be equivalent, but the equivalence is one such that you haven't even fully interpreted or defined one theory without also interpreting and specifying its dual theory. The next point is that in the actual practice of research, we see a very delicate interplay that's based on this idea. So, for instance, in that 07 paper, Witten tries to explain what the couplings of the bulk theory, the gravity theory, should look like. And the way he tries to do this is he starts from the conformal field theory side, and he says, look, the C theorem of the conformal field theory side tells us that the central charge has to be a constant. And the central charge is going to come from the couplings of the gravity theory. So somehow we have to get these couplings to be quantized. And he then gives a topological argument for why the couplings should be quantized, based on the first Chern class of a closed manifold. And then he goes back and uses that to constrain the conformal field theory. He says, we didn't know what the exact conformal field theory was, but now, I've done this work on the bulk side, and I can show that the couplings should be integer multiples of 24. I'm going to go back and look for conformal field theories that satisfy that description.
If you want to leave 50 minutes for Q&A, you should
stop. Okay, yeah, I'm going to wrap up. Yeah. So more generally, I've got 2 more slides. So more generally, in the ADS-CFT correspondence, the main formula that people use for calculating correlation functions on the boundary side, using classical supergravity, is a formula that relates the observables through coupling fields in the bulk to fields in the boundary. So fields like the gauge field on the bulk to the current for symmetry, the global symmetry in the boundary, on the boundary, and a metric in the bulk to a stress energy tensor of the field theory in the boundary. Again, the boundary conditions of the theory are in part defined or interpreted by means of its dual theory. So in closing, let me just quote Nick. When a new theoretical concept is formed, we understand it in part by understanding its logical place in relation to the already understood concepts of an existing theory. Holographic duality offers a novel version of this. We understand concepts which are only partially formed in a theory by embedding them in its dual theory, and vice versa. Indeed, this statement can in some sense be said to apply to the theories themselves. I can expand upon that during Q&A. Finally, just a heuristic level, it could be a very useful heuristic tool for motivating development of each side of the duality, which of course rests in part on the plausibility of the duality. Thanks for your attention.
So we have about 50 minutes for Q&A. Dave.
Yeah, can I see that Whitman quote again?
Sure.
I'm trying to make sense of it. And, so one way of understanding this, and you tell me what is the wrong way because I feel like it doesn't fit with what you're saying, but I mean, one way of understanding it is that we don't get the physical meaning of three-dimensional gravity. We know that there is a sort of theoretical equivalence between 3D gravity with negative lambda and its dual CFT, and so in those conditions, negative lambda 3D gravity is a notational variant of dual CFT, and so in that case we know the physical meaning of the theory because it's just a CFT written in a different notation. I mean, is that not what he's saying, or?
So were there other versions, or was that the only version?
That was the only version. That was the version that I was thinking made the most sense to me. I didn't seem to fit with what you were saying.
Right. So I don't think it's just a notational difference. It's not so far from what you just said. So I think the way to hear it, and I'd love Jeff to comment on this too, is that look, we don't know what the quantum dynamics of 3D gravity are. So if you look at just like the classical theory, there are no dynamical degrees of freedom, right? So we don't know what the quantum dynamics are. On the other hand, we know if it's true that it's dual to a CFT, we know how to formulate dynamics in that CFT. So in a sense, we can solve the dynamical problem for the CFT. Of course, there's a further question of how to relate that sort of thing back to a detailed story on the 3D gravity side.
Okay.
Yeah.
Well, I see. So the analogy with the S matrix then that the initial state has a corresponding state in the CFT. The final state has a corresponding.
Yes, that's exactly. Yeah, I think.
And we use the dynamics of the CFT to tell us which leads to which. So then we have
So like I said, there is a problem with trying to relate this to the details on the 3D gravity side, which is very much like the issue of trying to solve the black hole information loss paradox by saying that, look, the CFT the conformal supersymmetric gauge theory is unitary, so obviously unitarity isn't loss. You haven't actually, you can say this, but that doesn't tell you anything about the details of how this is true on the gravity side, right? So Jeff, would you like to comment?
I think what you're saying is correct. I don't think I have anything much to offer. Okay, Ellen.
Yeah, so this is mostly clarification. I was puzzled by the maths right at the end between the objects on the boundary and on the bulk. So these, so you've got this correspondence between G mu and T. Do you mean to have the same coordinate variables there? Obviously not, right?
Yeah. So the way I obviously didn't write up the whole thing, but the way this actually happens is that you look at the path integral of the quantum gravity theory and the bulk, whatever that is, right? So no one pretends to know what that is, and then you then look at what happens when it tends towards the asymptotic boundary, and it should coincide with the field theory path integral. And what you do is do calculations in that path integral. You put in these couplings, so G mu nu lowercase, T mu uppercase mu nu, in the exponential of the path integral.
Okay.
Yeah.
So they do in the end have the same dimensionality.
Yeah, they do the same. Yeah. Right.
Because it looks
but
very
obviously this will be contracted in that exponential. Yeah.
On the other.
Yeah, just a clarification. I'm not sure. Can you explain to me better what exactly one would like to compute on the 3D gravity side that cannot be done in the positive cosmological constant case? Which basically means what exactly is wrong with or missing in the definition of 3D quantum gravity positive cosmological constant as the Touré-Biro invariant? Because that, at least for given boundaries, it's a very well-defined quantity, so at least the definition of the theory should be okay. maybe just not.
Yeah, so you just get these topological invariants, right?
I don't know what that is. What is it you would like to compute and you don't know how to do it?
So I think that Witten's point there is that you don't get a dynamical, you don't get your hands in the quantum dynamics for...
Which quantum dynamics is a topological theory, so it only admits positive constant curvature solutions. So there are no dynamical propagating degrees of freedom. Without matter, if you were walking to matter, then of course there are lots of more stuff.
Yeah, so presumably, the CFT will have in states and out states. So presumably, the correct CFT dual will correspond to something that has matter fields on the bulk side, and but we don't know how to construct that
But
at the quantum level, right?
Pure gravity in the bulk.
It's not pure gravity in the bulk.
Matter
Yeah.
in the bulk, we don't really know how to condense that theory, and so I go to CFT. But for pure gravity, there's not much to compute in the first place.
Yeah, no, I agree. So this is, Jeff, would you like to comment again? Actually, this is something you probably...
Maybe I'm misunderstanding what
I mean, in ADS you can look at the metric and that's some asymptotic behavior. So you can fix that asymptotic behavior and then ask what the path integral is for the theory of that asymptotic behavior. And that computation is supposed to map to the correlation function stress tensor in the CFT. So if you specify, that's sort of observable.
So the additional is boundary the path integral to the gravity function.
I'm not quite sure I understand the notion of theoretical equivalence that we're supposed to see in action here. And mostly that has to do with me not fully understanding the physics here. So maybe, help me a little bit. Would it be unfair to say that one reason why these other more precise notions of theoretical equivalence are inapplicable is because we don't really have a full understanding of what the theories are yet, so that they don't even kick in? Or would that be unfair?
That's in part true, although there's all sorts of other cases of equivalence in physics, which I think you'd be hard-pressed to formulate as categorical equivalence.
Right.
So that's something...
Oh, by categorical equivalence, by the way, you mean the Morita equivalence?
Well, that's one form of it, but I just mean the very basic thing.
Oh, okay.
Yeah, where
No.
you have,
Categories.
roughly speaking, an isomorphism of functors between two categories.
Okay.
Right? Yeah. But, sorry, I think I answered the second part of your question, but not the first. You want to say the first thing again?
What was the first? Did I say two things? Well,
Say two things?
You said maybe you didn't understand the physics.
maybe you want to comment.
Yeah.
Yeah, okay.
I don't. So maybe this will help. So this idea that one of the interesting aspects of this sort of duality is that there are elements of a theory that are not even fully physically interpreted or understood until you've explored the dual theory. That idea, I think, is distinct from whether or not you can formulate it in terms of an equivalence of categories. Does that help?
Yeah.
So in the case of Chern-Simons theory with compact gauge group, which is not this case, Anton Kapustin and his collaborators have managed to give some kind of categorical, see, it's not an equivalence, but basically they've managed to do things in a categorical way and get the holography out of it. But it's not, I don't think it's an equivalence of categories. It's something a bit different, yeah.
To follow,
Follow.
yeah, so, I mean, you probably already know this, but, one can weaken categorical equivalence or require that you don't preserve all categorical structure, and one might interpret this kind of situation as exactly the situation where we have some theory, we don't know, because we don't know what's physically relevant and what's physically meaningful, we don't know what categorical structure needs to be preserved. And so we're kind of exploring in the range of we're using the assuming, taking the full strength categorical equivalence, mapping over to where we do understand what's physically relevant to tell us more information about what we actually don't care about. But that would just be an extension of the categorical way of thinking about equivalence, not really an example of it not being.
Yeah, so in the Kapustin paper, he does use two categories.
Okay, right.
Is this a follow-up?
Sort of. It's about theoretical equivalence in general.
Okay.
I just wanted to pick up on your remark along the lines of we don't understand theoretical equivalence except perhaps as categorical equivalence in the light of the model isomorphism criterion being wrong. It's like an old man question. Long ago, in the syntactic view of theories, people said, let us model two theories as being equivalent if each of them is a so-called definitional extension of the other, meaning that you can add definitions of the predicates of the one to the claims of the other in such a way as to deduce all the doctrine of the one, and vice versa, right? Now that, I take it, won't produce model isomorphism under the rigorous reading of that I think Halverson deploys, namely, a model isn't just a set with some structure on it. The structure is labeled with which vocabulary items are being interpreted by that particular 2-place, 3-place, whatever relation. So since the two theories have got different predicates, you have to do a bit of talking about mapping the one into the other, informally speaking, by using the definitions that I mentioned as being used to grab the one from the perspective of the other. But surely one can add a little wrinkle to model isomorphism as rigorously construed with keeping track of every darned little vocabulary item's initial presentation, and parley up model isomorphism into a supremely compelling definition of theoretical equivalence. After all, anybody's bound to say that a theory is equivalent to itself, which clearly corresponds to having the same set of models as oneself. So, I put it to you, mutual, being each other's definitional extension should be a good concept of theoretical equivalence. And I conjecture that in all this physics stuff, we could probably deploy this good old traditional syntactic view of theories in order to make sense of what these clever clogs in ADS-CFT are talking about.
Right.
There's actually a very recent, if I may interject, a very recent reaction to Halverson by Clark Gleamore showing how this can be done in a semanticist's way of without this overly narrow understanding of model isomorphism.
Can it be done in a semanticist way or syntactic?
Yes, well, at least part of the problem, the one problem that you addressed. Another part of the problem cannot really be done. You have to look at more than the models, the set of models. You have to look at the structured set of models. That point that Halverson made, I think, still stands.
It still stands.
That, I think, yes, but I see no reason why the semanticist couldn't parlay up some reasonable criteria to capture that as well. But now we're getting very abstract in this discussion.
Can this discussion be translated to the next physicist? I don't know.
Sorry, let me just say something super quick about that.
Johan, very quick, or we?
Yeah, I'll say something super quick. Look, so yeah, I totally agree that you can write, all the axioms, definitions, so on and so forth, and then deduce, the dual theory. That should be possible. Group things in the right way, although it would be hard to write out everything syntactically. The reason that I chose to focus on this case of, thinking about a theory as a category of models wasn't because I thought that's the only way to do it, or that the syntactic view is wrong. It's because this is the way that's kind of native to most modern math. And so I feel that if we want to be in dialogue with physics, to some extent we should try to think along those lines, right? So that's not to refute what you said, it's just to agree and change directions.
So I would let Johan ask the question, except that you really have to go to the taxi.
Sure.
So let's...
There's a taxi waiting outside.
Yes, let's